Hello everyone, my name is Anushka Papori, and today I'm going to present my paper on general adversarial networks in image direct generation and recognition. General adversarial networks, or GANs, were introduced by Ian Goodfellow in 2014. They consist of two deep neural networks, the generator G and the discriminator D. The model is formulated as a zero-sum minimax game between G and D. G tries to generate synthetic data, and D tries to identify the generated dataset as real or fake. D tries to maximize the loss function while G tries to minimize it. A Nash equilibrium is reached when each player does not need to change their actions. In other words, D accepts the synthetic dataset is real. What's basically going on is that G is continuing to generate data so that it can fool D into thinking that the data that G has generated is in fact real. GANs have various applications and variations. One of them is style transfer, which imposes stylistic attributes of one image, called the style image, to another image, called the content image. This model applies the artistic and textural elements of the style image onto the content image. Super resolution takes a low resolution image and creates a high definition version of the same, including higher resolutions. This is very useful in medical imaging, astronomical imaging, etc. Image-to-image translation converts types of images while preserving the underlying structures and context. This model uses paired or unpaired training samples. It's very useful for converting hand drawing to accurate images, grayscale to color, etc. GANs are obviously very useful in image generation. There has been many improvements in them over the years through different research papers. It has improved their training stability, the consistency of generated images. There has been many different kinds of images that can be created and many different uses of GANs that have been added over the years. Deep convolutional GAN, or also known as a DC GAN, was introduced by Radford and team, and it introduced a convolutional networks in GANs. This model used a deconvolutional generator and a convolutional discriminator. It greatly improved training stability and consistency of generated images. The conditional GAN, also known as a CGAN, was introduced by Mirza and Asandero and team and incorporated conditional variables into GANs. This model improved controlled image generation using specific attributes of images. The progressive GAN was introduced by Karras and team, and it introduced incrementally increasing resolution during training. This significantly improved image quality, training stability, and variation of generated images. The uncontrolled variational autoencoders, also known as VAEs, were introduced by Kingba and Welling. And although this is not a GAN, it is highly influenced by a GAN research. This is a type of generative model that learns a latent representation of data. This latent space can be manipulated to generate new data points. The Wasserstein GAN, also known as the W-GAN, was introduced by Arjosky and Chintala. This paper introduced the Wasserstein distance metric in the adversarial training process instead of the Jensen-Shannon divergence. This model created a meaningful loss metric, leading to better convergence of the training process, and this model was also less prone to mode collapse. The cycle GAN was introduced by Zhu and team, and this paper introduced a novel idea of using two generators and discriminators that worked in a cyclic manner to convert images from two different domains back and forth. This model uses the cyclic consistence loss, a key innovation for accurate translation of images from different domains or styles. This model can use paired or unpaired datasets, which gives a high degree of flexibility. Isala and team introduced the pick-to-picks for image conditional image generation. This uses a UNet model for generator and a patch GAN for the discriminator. The model uses an L1 loss, which is a pixel-wise difference between the generated and target images. This leads to better accuracy. This is a groundbreaking model that can be used to colorize images, translate sketches to realistic images, and create maps from satellite images. There are three style GANs currently. StyleGAN 1, which was introduced in 2018, StyleGAN 2, which was introduced in 2020, and StyleGAN 3, which was introduced recently in 2023. Karis, Lane, and Ayla and team introduced the idea of using separate generators for features and styles. This model uses the progressive training process from low to high resolution images. This paper introduces an adaptive instance normalization, also known as ADA-in, that allows for a style generator to inject stylistic information into the features generator's output. This model has achieved unprecedented levels of photorealism and diversity. The Big GAN was introduced in 2018 by Brock, Donahue, and Simoyan, and this model was applied a large scale of training using large datasets, such as ImageNet. This model used self-attentional modules with a large batch size of 4,096. This uses spectral normalization on the discriminator to stabilize training and to prevent gradient explosion. This allowed for a much wider range of visual patterns and thus creating more realistic images. The StarGAN was also introduced in 2018 by Choi and team, and this used a key innovation, a single model to translate between different domains, unlike previous models. The generator generates images based on a given domain-specific label. This model introduces domain-specific Latin space that captures the essential features of each input domain. This showed impressive results in image-to-image translation and multi-domain translation. The temporal coherent GAN, also known as the TECO-GAN, was introduced in 2018 by Xu, Shi, and Meyer and team. Standard GANs struggle with generating temporally coherent outputs in videos. Standard GANs have frequent artifacts and inconsistencies across video frames. TECO-GAN incorporates a temporal coherence loss that penalizes inconsistencies between the generated frames and encourages smooth transitions between them. The model's loss function can use a recurrent neural network, an RNN, to analyze the temporal dependencies between frames and guide the generator's outputs. The model is progressively trained, starting with generating low resolution video segments, gradually increasing the resolution. This model produces significantly higher quality video compared to its standard GANs with smoother transitions and reduced artifacts. Feature matching GAN was introduced in 2018 by Salimans and teams. They showed that GANs can be employed for semi-supervised learning. The model minimizes the statistical difference between the generated and real images and uses L2 distance or the Kullback-Leibler divergence. This model avoids the problem of overfitting in older GANs. The triple GAN was introduced in 2017 by Xungxuan and team, and they integrated the conditional GAN with a classifier, resulting in a three-player game between the generator, discriminator, and classifier. This model was an effective combination of the data generative and discriminative distributions. The unified model showed remarkable improvements in semi-supervised classification. The self-attention GAN was introduced in 2018 by Zhang and team. They introduced self-attention mechanisms in both the generator and the discriminator. This model allows the network to focus on long-range dependencies within the image, and it also avoids the problem of overfitting in older GAN models like the feature matching GAN paper. The auxiliary classifier GAN at GAN 2016 was introduced by Odena and team. They used an auxiliary classifier along with traditional GANs. This model allows the discriminator to identify the class of the input data. The dual-ruled GAN, DR-GAN 2017, was introduced by Tron and team. They introduced the idea of generating multiple images of a subject from a single input. This greatly enhances recognition rates. The categorical GAN, also known as the CAT-GAN in 2019, was introduced by Springer and team, and they focused on unsupervised learning and semi-supervised categorization of data. The discriminator made to predict a categorical distribution over the data. This model was very effective in distinguishing categories. Obviously, GANs are not perfect, and they have many challenges. For example, mode collapse begins occasionally. The generator begins to produce a limited type of output, regardless of the various input noise. The generator might find it optimal to generate fewer kinds of output. This hinders the ability of GANs to produce a broad spectrum of realistic data. Richardson and Weiss in 2018 proposed a number of statistically different bins, the NDB score as a countermeasure. Another big problem is training instability. It's a significant challenge across GANs. Heavy oscillations or non-convergence during the optimization process can occur. This instability can produce suboptimal or unrealistic data. Strategies include meticulous hyperparameter tuning, gradient penalties, and alternative loss functions. GANs are very, very powerful, and therefore they can be used in new applications, frontiers, and have opened many areas of research. For instance, GANs can be used for medical image analysis, applying GANs to generate synthetic medical images for training diagnostic models and personalized medicine applications. GANs can also be used in scientific discovery, employing GANs in scientific fields like drug discovery, material science, and climate modeling to generate new data or accelerate the research process. GANs can also be used in explainable AI, or XAI, exploring how GANs can be used to explain the decisions made by complex AI systems can improve transparency and trust. It is very important to consider fairness and ethics in terms of GANs. We must address potential biases and ethical concerns associated with GANs, including developing fairness-aware training techniques and mitigating the risk of harmful outputs. Additionally, research is ongoing in areas like federated learning, which is adapting GANs for collaborative training across decentralized data resources, multimodal learning, which is combining GANs with other modalities like text and audio for richer representations and generation, and meta-learning, which is developing GANs that can learn how to learn better, adaptation to new tasks and data. Thank you so much for this opportunity. I am truly grateful that as a high school student, I am able to publish a paper in such a prestigious community, and I'm able to share my passion in artificial intelligence, neural networks, and general adversarial networks with all of you. Thank you so much.